Then let's start with this example, cold formed design. And I show you this cold formed design in our new application SHAPE THIN 9 and subsequently in our RFEM application inside the Steel EC3 module. But before we start in SHAPE THIN, for this we open a new sheet, maybe a C section, and run several tests to see the effect of this program. For this, that you see how it's working, I model at first this cross section. Yeah, we start with a node, of course. Then we copy this node maybe here in Y direction, almost 40 millimeters one time. And then we copy these two nodes in Z direction with almost 100 millimeters. Yes. So this is maybe the pure geometry of this cross section. And we connect these four nodes with an element with the thickness of 1 millimeter. It's pretty thin, I would say, with a, let's say, standard steel, and produce such a cross section. Yes. Oh, one element is missing. We add it here. So, okay. Then we have here these three stripes, which creates together this channel cross section with the thickness of 1 millimeter. And independent if it have maybe a thickness of 100 millimeters or 1 millimeter, we want to design it and we want to see how the different methods are working and which one is good or bad for this cross section. So, but at first, to see the basic reaction, I apply a bending moment in the way that I get compression on the web here. So yeah, I create here a load case, maybe with bending. As load, I use here maybe this tabular input for member 1 on x place 0. All forces I write down to 0, but I apply this bending on the y-axis. I think this is more clear. So on z-axis, so here this is still 0, and here we use minus 0.02 kilonewton meters. So when I apply this load here, bending load on the cross section and calculate this cross section, we get a multicolored picture. We get a dark blue web, what means we have compression on it. The three legs of this cross section have tension. And, oh, sorry, dark blue is here the stress and the legs have tension. Yeah, I just wondered why it's negative. And with this load, we can see I can increase, of course, the load. Then we get here bigger values. But finally, if we compare it to the limit stress, to the yield stress, the utilization will be go over 1, so we can't design it. But anyway, the issue appears that we have no feedback if the cross section will buckle. If we imagine that this cross section have only a thickness of 0.1 millimeter, so we can change it infinite. And therefore, I apply a second method, the standard Eurocode 3 method. For this, I activate effective cross-section values in the general data, what is at least a basic function in SHAPE THIN. And now I get here the option below calculation parameters, below this sheet C to T parts, and can assign the standard Eurocode design here according Eurocode 3.1.1 and 1.5. So if we do this, The program assigns here such typical C to T stripes. This stripe means it is fixed on this corner and free on this side. This is fixed on this corner, and again here also fixed on this corner, and here fixed and free. If we run the analysis with this bending load, what I defined with this 0.2 kilonewton meters, we get at first the elastic stress, but if we change to effective cross-section values, we will see the program cuts out a specific part of the web. What means that this part will buckle and he will remove it, and the, let's say, the power of the bending moment have to distribute on the upper and lower part of the cross section. And this results finally in a bigger utilization. So we are over one. So we are 5% over 100%, what is not good, let's say. And we have to think about how we can solve this cross section. And for this, I can offer now a new method and a new design method. I change here now again in the calculation parameters from the standard Eurocode solution to the code formed design solution according Eurocode 1.3. Additional, I say, please show me the RFEM submodels, and I confirm this setting. Now the program deletes the results, of course, but we get now here two more options. I can simulate a stiffener in this cross section. For this, and with this stiffener, we have the chance to, let's say, to improve this cross section without increasing the weight enormously. For this, I divide the web part into with 3 nodes. Here, then that I can easily change it, I move it to the center. Now I move down the upper node to minus 10 millimeters, for example, and the lower node to 10 millimeters. And here we produce now a small stiffener by moving this node in Y direction. So now we have almost the same cross-section shape, but we have to introduce here the stiffener. And here I can select the stiffener by drawing a window about. Okay. And now the program realizes that this is an internal stiffener. And now we draw this C to T stripes globally above this cross section by assigning panels. And here I assign the first panel. Okay. Then I assign the second panel. Okay. And I assign the third panel. Okay. Now I have these 3 panels, and you can see here in the in the second panel we have also this stiffener. And with calculation of this, let's say, cross section with improved data about stiffener, I can calculate or I can consider an exact model behind and can have the chance to get better results. I start the calculation. Now the program syncs, I think. I hope. Now the program is modeling this cross section inside, or let's say in a hidden RFEM application, loads this cross section with a unit load and envelope on these places where the unit load is defined, a unit spring for further calculation of the stiffness of these buckling panels, at least. So on my second monitor, I see already something, and now he's already finished. So a colored picture appears, but this is maybe always. But what is interesting now, we have now effective cross-section values. And here you can see that the program, the same like for the standard Eurocode solution, realizes here in the mid part, let's say, a critical part according to compression, and produce on this mid part subsection property calculation. What means he cuts out this value and calculate the stiffener of this, the spring of the stiffener here by using this, let's say, stiffener displacement and enveloping from this a stiffener spring and calculating from this maybe this critical stress. What could be visualized in this picture, I think it's more clear if you see this. This is now the sub calculation behind, where the program is calculating one stripe of the cross section by applying a unit load. And if we calculate this unit load, we get here a deflection of the cross section by considering the complete geometry, and get here the deflection for this applied load of 0.14 centimeters. And this information is now also mentioned here, what leads to the final critical buckling stress of these panels, from which the program again can calculate the resulting effective cross-section values. You can see that the facet of this whole procedure is that the program reduces the thickness of this intermediate stiffener part to get real cross-section values, what ends up in, let's say, reduced cross-section values here, maybe with 1.70 square centimeters for the surface, and for example here for the bending about weak axis with 2.52 as stiffness. So this is results as cross-section values, and of course the utilization is now exactly one. This was I produced this example to get exactly this curve of results. So I want to show you that we can calculate such a channel cross section, elastic, with elastic stress distribution, and it's good, but we don't consider the buckling effects. We can calculate it with basic Eurocode, but it will buckle. And with this cold formed analysis method, we can consider a stiffener to maybe to rescue this cross section. And the same method is now also available not only for one X-place of cross section, then also for all X-places on a member in RFEM. And for this, we open an RFEM sheet, go here to a new model, make here code formed, and go here the axis upward, and okay, yes. And now we can model the same cross section, maybe store this at first, save as on the desktop. And now we go back to RFEM, yes, and create a new member with the same cross-section from SHAPE THIN with the code formed properties. I can load it here, and now we go to the desktop, and it was, I think, here's this one. Open. Now we have this already modeled SHAPE THIN cross-section. We can assign here the right material. It's not 355, then it was here standard steel according Euro norm standard, yes, okay. And now we can place the member in this space. To reach this defined bending moment, I need a 2-meter long beam supported on two supports, right and left. To prevent rotation about our axis, I support here the 3x axis. And now we can apply a load of 0.4 kilonewton per meter about the big axis. In y direction, minus 0.4. And now with calculating this load on this member, I expect that we get again a bending moment of 0.2 kilonewton meters in the middle. Let's check. Members MC, so we have here a bending moment of 0.2, and the stresses to check if we applied it right, we get on the back in the web again compression stress. So far it's good, and now we can do the same code form design with all properties what we defined in SHAPE THIN for the complete member in Steel Easy 3 by applying this member for design. I use here Euro norm according to defined material for this load case. And to compare results without stability, I deactivate all stability designs and activate this add-on RF steel cold formed sections for this cross-section design and calculate. And now the program gets a utilization. It's better than in SHAPE THIN. I explain it why. But at first we take a look what he did for this cross-section design. He wrote down everything what he have, maybe material properties, cross-section properties, and so on. But he calculate effective cross-section values for the axial force, for bending force about y-axis, and for the bending force about z-axis. Because I applied only a bending about z-axis, only this last chapter is important. And here we get again our well-known effective cross-section properties for maybe the cross-section surface and for the second moment of area. And according to this cross-section, the program calculates finally stresses and compare it to allowed limit stress. And because we know that the cold formed process increases the yield strength by every corner what is maybe pressed into the metal, we can increase the, let's say, average yield strength. And this is the effect why we get now a better solution than in SHAPE THIN, because here we have not now 25 kilonewton per square meter and not 23 like common in SHAPE THIN. And this helps now to make this pretty small thin cross sections calculatable for the full model in RFEM, not only for one members and for a complete structure. And it's your game to assemble these members together and the program DLASY3 with, let's say, this special cross sections from SHAPE THIN. Additional with this add-on function code formed for DLASY3 makes it possible that you can design such type of models, not only for, let's say, cross-section designs and also with stability design. And this is now the end from my presentation, and I give back to Andreas.